Everyone, here we are at the last day of the workshop. It's been both very packed and gone by very quickly somehow. Day 4 is a little bit shorter, but gives us some more time to think about our data, how we examine our data, and what kinds of outcomes you're getting as you're making progress on your take-home projects. One thing I want to mention, just as a reminder for those in the room, make sure that you've logged into Zoom with your computer muted so that you can interact with our virtual attendees through the chat, that sort of thing. And then, since we are at the top of the hour, I'll just go ahead and dive into our morning session where we get to talk about something. Well, I keep saying near and dear to my heart, but literally this whole workshop is. But in particular, open data is incredibly important, and it's good to think about what we mean by that. So I'd like to invite Scott Collis to come up and chat with us and open our morning session to discuss open data. So let's welcome Scott.
This has some wonderful symmetry to it, doesn't it?
Yes.
Given that it was only a couple of years ago I was introducing you at the AMS. All right, let me go here and share my screen. Get rid of that. Okay. Oh, actually, let me get rid of my reminders as well, so we don't have that down in the bottom there. Cool. Okay. Thank you so much, Kim, and hello, everyone. I'm Scott Collis. I am an atmospheric scientist and department head at Argonne National Lab. I wear many hats. As I said in this presentation, this is on behalf of many others. I'm going to talk a lot about other people's work. I'm just the spokesperson here. I've also taken a slight page out of Susan's playbook here, and I kind of picked my own title. I was asked to speak on open data, opportunities and challenges, but of course I wanted to think a little bit bigger and talk about open science in general. The ultimate title to my talk is How Software I Led Got a Mention in the New York Times and Why I Actually Thank Unidata. I have a long history of being a Unidata user, despite the fact I am at a DOE National Lab and not really actually the target for Unidata. When I first arrived in the US, I was given the task to set up a forecasting system for a DOE field project, and I learnt the joys of LDM. In doing this, actually, funny enough, working a lot with folks from COD in doing it at the same time for bringing in next-red data, observations, and others. So I was kind of taking down some notes, trying to, well, why am I here? Why am I taking 30 minutes out of your time? What should I be talking about here, given that this is a very well-educated audience when it comes to computer science data, software, and so forth. So I kind of came to the conclusion that I'm really here to motivate this workshop audience, you, to advocate and contribute to open science, because in the end, open science is just better science. So first, let me actually tell you a story about my story arc. Again, I'm really grateful I'm going later in the workshop because this is probably version 4 of my presentation now as I've been learning. The story I'm going to tell you throughout the whole presentation will be about people. And so despite all the titles I am known by now, it was really that Python guy who goes on and on about open science. I actually was neither a Python guy nor an open scientist at the end of my PhD. I did a PhD in high-temperature plasma physics, working on a magnetic confinement device, working in IDL and sharing none of my code and none of my data. When I actually joined the Australian Bureau of Meteorology, they didn't have an IDL license. So I needed to learn this other programming language. Look, oh my goodness, Python's free. I can get in and I can start coding this. The very first bit of code I wrote in Python was actually a meta parser, so I could plot some of the observations from one of our local airports out. But on moving to the US, I learned about the Programming with Scientific Python conference held in Austin, Texas every year. And I thought, yeah, okay, I want to go to that because I'm a person who uses Python for doing science. And oh my goodness, my mind was blown because there were just rooms of people working together on the same code base, irregardless of where they are in their career. You had professors working with students, you had people from labs working with people from community colleges, all just kind of pulling in the same direction with no financial imperative to do so. And I kind of went, you know what? I want some of this. So that's actually where I learned about GitHub, and decided to make all the code that I was working on open source and open science. This talk, I'm going to address a couple of different statements. One, I'm going to show that open science creates communities of practice. I'm going to show open science is an interagency glued, and often this collaboration across agencies, as I'm kind of demonstrating here right now, is much more efficiently done at our level than at the level of a programmatic level. Open science is an organic way to achieve research to operations, and open science does need care and feeding. I really love this picture here that's often shown when we talk about open science. You know, free beer, and of course the joke is that that beer is free, but it costs 500 yen. Open source software is a great example because it illustrates an issue in the English language, that our word for costless is also our word for being free. So open science is free as in libre. It is definitely not free in terms of cost. It costs money to make open data and make open source software and so forth. First of all, I want to ask you a question. When I say open science, what is open science? And the people at the back, if you can let me know if there are any answers online or anything like that, but put your hand up, let me know what you think open science is. Otherwise, I'll pick on people. Mike, what do you think open science is?
I think open science is the removal or the absence of limitations in availability and, to an extent, usage, appropriate usage.
Any other opinions on what open science is? Well, I got an idea. Let's ask ChatGPT what it thinks. And it kind of, and by the way, again, this is an example, this is kind of a joke, like Nick's talk before, because this is a ridiculous slide. I'm not expecting you to read all of this. But it does kind of hit the key areas that we really define open science as, which is open access, open data, open methodology, open peer review, and citizen science. But you know what? That's too much information here. So I then asked ChatGPT, what is open science in the form of a haiku? And I thought this was much better there. So, knowledge unleash, science secrets set free, open minds take flight. It's like, now we can all be an artist. So, yeah, one part of open science I talked about before is open data, and since I was asked to speak about open data, I better at least touch on that. And the question is, open data, is it sufficient? I can take my data, I can put it on an FTP server, and I can share the link and say, you're free to share the link. Technically, that's open data. But it's really not going to impact science nor move the needle in terms of its usability or what science can be done by other people. And that's where we come to FAIR. And I know there's going to be a couple of people talking about FAIR today, so I won't belabor this thought. But FAIR stands for findable, accessible, interoperable, and reusable. And that, to be truly useful, you'd need your data to be fair. A great example of this is a netCDF file meeting the CF standards, fully self-describing, sitting on a thread server where the location of that thread server is well advertised, well known, sitting on repositories, at least findable on Google. But thanks to Jupyter and Pangeo making tools like Binder Hub, FAIR can go to the next level. Because I can now go and write a cookbook, and I've become a huge fan of cookbooks, and disseminate that cookbook, which not only tells you how to access the data, shows you how to use the data and give you some shovel-ready examples you can build your science on. So here's my first kind of attempt at being, try to stir the pot a little bit. I'm going to posit, and this is what I was talking about before, that single author papers can be, and of course I'm kind of pulling my punches here because I'm going to say often are, disingenuous. If you think you've gone out and written this paper and you've not had help from anybody, maybe that was possible back in the days when you used to sit down there and just scribble equations on a board, but increasingly it's just not possible to do something that doesn't involve collaboration, doesn't involve building your science on top of somebody else's, and increasingly without using data or writing at least a line or two of code. So I'm positing increasingly the code we write is our science. The paper we publish is more of an advertisement for what we've actually done. So tools and data sets, so by sharing your code, you're actually kind of sharing the methodology of how you did your science. And that's why tools and data sets are increasingly drawing people in. People will actually congeal around working on a data set together or contributing to a code base together. This is what creates communities of practice. Matplotlib is a great example. When you see the servers that they're set up, the conversations that go on, Matplotlib has really revolutionized the way in which we address issues with color blindness, color vision deficiency, by giving us a way of making color vision deficient compatible color maps. And that all came out of that group. That was actually research done by that group and pushing that out into the community. So what are, in this group here, in the atmospheric and earth sciences, some example of communities of practice that have congealed around, say for instance, some of the community software toolkits? What are some examples people can think of?
I think Pangeo.
That's a great one. I completely agree. Yes?
Project Pythia.
That's a fantastic one. Another example I can think of, for instance, is MetPy. And there are some of my examples right here. MetPy, Pangeo, PyTroll, the satellite community coming together around PyTroll and SatPy. An example I'll talk a lot about from my own experience is Open Radar Science. Tobac is a cell tracking toolkit that's out there. And I've got like MetPy Mondays, I think is just a fantastic example of how a lot of these open source toolkits transcend the code itself when you go into science conversations. What's the best way for calculating CAPE, for instance? And how am I going to represent that in my toolkit? Because in the end, by sharing code, you're actually sharing how you're doing this science and you're creating those communities of practice. So Open Radar Science. So I lead the Python ARM Radar Toolkit. I really kind of should put more in there about that, but when we first started with sharing our code in Radar Science, we found there were a couple of other toolkits out there. There was the Radlib toolkit being run out of Europe. There was the BoltRad toolkit, which ended up moving to Canada, to Environment Canada, and there was the LROS work that comes out of NCAR, led by Mike Dixon. And we said, you know what, we really should be working together. So for the last 10 years, the leads of these software packages have held Open Radar short courses at the AMS and European Radar conferences. These always finished with an interoperability exercise where we actually did an analysis of a radar dataset that used every code base which we were teaching. This was fantastic because not only were we teaching our students a diverse range of skills, it actually really forced us to actually make sure our toolkits were intercompatible. Last year's European Radar Conference, well, this is a picture from the Radar Conference in Locarno, Switzerland. Really good place to get your mind thinking when you're surrounded by the Swiss mountains in the south of Switzerland, which is kind of more like Italy than Switzerland. This is actually at Medio Swiss's headquarters down in the south of Italy, and we're standing under grapevines there. Of course, there is Max in his Hawaiian shirt, and they actually had, you could eat the grapes off the grapevines. But this led us to thinking, okay, we've actually been doing it the wrong way around. We shouldn't be finishing with an intercompatibility exercise. We should be taking the I/O layer from all of our projects and making a package that had a unified I/O layer. So basically, you're able to read your radar data in to this, and then you can then hang analysis codes from PyArt, BoltRad, RadLib, and so forth off the end of that. And this actually led to XRadar starting, which actually is all based around X-Array, and Data Tree, which is again a wonderful thing that's come out of the Pangeo group. And so what really also came out of this, and these slides are of course on the Google Drive, so I don't expect to write this down, we also realized that a lot of the questions we were getting on GitHub had nothing to do about our software packages at all. They were like, how do I retrieve rainfall rate from radar data? They were actual radar science questions. So we've actually created a discourse where people can go and ask these questions, and we can then have a building database of questions and answers that people can just point to. Again, this is an example of one branch of open science, which is open educational materials, really democratizing this knowledge. So, to my alt title, PyArt plus NextRad equals democratized radar science, or how the New York Times ended up using the software package that we lead there. So another huge shout out to Unidata. The work they did in getting NextRad out of NCEI, used to be NCDC, onto Amazon Web Services, Google Cloud, and so forth has created a game change in how NextRad data is used. With PyArt being open source and NextRad being on the cloud, it has removed many of the barriers to using radar data. Python is a popular programming language. It is a language that is not only used by us, it's also used by the graphic artists at the New York Times. So they're actually then able to take radar data from, this was one of the, I can't remember which Pyrocumulus cloud this was, I think it was from the campfire in California. They were able then to take the NextRad data, take PyArt, grid it onto a Cartesian mesh, which we spent a lot of work doing in improving our gridding algorithms. And then they were able to then make that into a format they could pass into the visualization software and create these really cool 3D ISO surfaces. And again, this wouldn't have been possible if we wouldn't have put our software out there and the NextRad data was on Amazon Web Services. So basically by having open source software and really easily available open data, we're opening up this data to new audiences who would not otherwise have used these data sets. Another great example I really like from PyArt is that we're seeing a lot more of the ecosystem community using weather radar data for looking at things like birds and insects. There was a really great paper published in the Proceedings of the National Academy of Sciences that looked at mayfly hatching and diurnal cycle in Canada and other places, again using data from NextRad and using PyArt there. So when you kind of look at PyArt citation, we published a meta paper back in 2016. It's up to 330 citations. So by the way, open science isn't only the right thing to do, it's really good for your career. I have benefited so much out of the success of open science there. So many of the papers that are citing this meta paper are not your traditional supercell, so on and so forth paper. They're other applications of radar data that probably wouldn't have happened without open source code and open data set. So on to one of my other statements, that open science is a great way to enable research to operations, or even better, operations to research or operationally directed research. Sometimes R to O can be really, really forced. You have a bunch of scientists who want to study esoteric things and they're told this has to be applicable. Open science, especially community-driven software, can act as an interface because researchers using the same software base and operational people using the same software code base can contribute to that same toolkit. So if someone's developing a new theoretical rainfall retrieval based on, let's say, attenuation in radar data, folks at NSSL and so forth can pick that up and use it pretty much instantaneously, especially with something like PyArt, which is really data model driven. We read all these different formats and represent it as the same data model in Python. Again, that's the idea behind XRadar. Something developed by the Swiss can be used by folks, by ARM, for instance, by us, with our radar system that's in Mount Crested Butte in Colorado. Radars, to a degree, can be kind of agnostic to where they are. There's a couple of papers, for instance, I really like that have been cited the PyArt meta paper. One that recently came out was actually about an open radar, open source data processing chain for an X-band network in the south of Italy as well that was using PyArts. So again, this whole idea about being about people, about these open science projects, building communities of practice, but building very diverse communities of practice. So let me survey you all here, because one of the other things I wanted to posit was about interagency science and how open science can help break the stovepiping of that. So who here's research, for instance, is supported by the National Science Foundation? What about the United States Department of Energy? So, NOAA. What about USGS? Okay. Throwing one out, the US Department of Agriculture. Anyway, what we can see here is this open science group, this ostensibly workshop that is supported by NSF is bringing together a huge diversity of researchers who are funded across the US weather science enterprise. And we see that, by the way, with things like Pangeo and all these other projects, because these, even though they will be kind of seeded by funding from a particular agency, they grow and they bring in contributions from an interagency perspective. And I worked at the DOE level. I've also interacted a lot with NSF, and there are huge difficulties in actually crossing the interagency divide at that higher level. It is much more efficiently done at our level. So I was asked by Mike and others and by Alex to talk about opportunities and challenges in open data and open science. I've gotten up here and talked about all the great things. I haven't talked about the challenges. So what are the challenges that I see in open science? One is making sure those of us who have decided to become open scientists can still grow and thrive in our academic and professional environments, that those contributions are valued, because let's face it, being closed grants a competitive advantage. I can have my own toolkit and I can say to everyone, it's the best thing out there. I don't actually have to prove anything, because you don't have access to my code. You don't know what I'm doing. You don't know I'm doing exactly the same thing that is in MetPy, for instance. But I can say, hey, you want my help, you write me into your proposal, we all get funded together, and I can string together a research group by doing that. By being an open scientist and putting everything out there, I have to rely on agencies and my employer seeing the value in me doing that. As I said earlier on, open science isn't free as in free from cost. We still need to build a much better practice for other scientists to cite our software, to cite our data, and building a practice of citing DOIs, because that just does not exist yet. Losing talent to the closed parts of the private sector. The machine learning boom means that, honestly, people can walk out of a place like Argonne, and we pay very well at Argonne, but they can double their salary by going to Google and other places like that. And Google, while they'll open a lot of stuff up, they definitely do not open everything up. And growth needs to be sustainable. One thing I've always said is projects need to be allowed to die. When someone has come across with something better, if we are in a safe working environment where it's not failure to let your project die, to go, you know what, this other package, it does it better, cheaper, than I am, I'm going to move on to another project now. We need to allow that in our workplace, and for that to actually be encouraged and not someone turning around and saying, you know what, you weren't good enough. Because there's always going to be someone better out there, and you might be better off contributing to that. I talked briefly about TOBAC, which is a tracking package. We led a package called TINT, which stands for Tint is Not Titan, that also did tracking of radar data. And TOBAC came out and we said, this is a better framework. We're going to merge our code in with TOBAC, and we're going to contribute to that. We do not need to lead everything. So wrapping up, all science is built on science that comes before. This can be very confronting to some senior professors out there. I'm sorry, your science is incremental. You didn't come up with that idea by yourself. Open science builds communities of practice. For me, it's just much more of a fun way of being a scientist. I don't have the mental space to keep secrets. I like to share what I'm hearing. When I hear someone has a problem, I'm like, oh my God, you should hear about this tool that I found that I want to share with you. I'll say to this audience here, contributions can be very diverse. Don't undervalue your contributions to open science. Write a cookbook as a companion to a paper you're about to publish. Respond to a discourse question. Ask a question. Asking a question can sometimes be the best contribution you can have to open science. Susan and I were just talking about the lack of braveness sometimes in people asking questions, because if you've got that question, many people probably have the same question, and by breaking the silence, you're doing those other people a huge favor. But I also understand that not everyone can speak with the privilege I have, being kind of white, male, mid to senior career, middle age. I've got it all going for me. So I can sit here and say, be brave, but I understand that there are barriers to other people. Advocate for open science with decision makers, and most importantly, mentor students so we can make more open scientists. Let's get the secret sauce out of the way in which we do science, because I've seen some of it and it's not good sauce. So with that said, thank you for listening to my story. There are my contact details there, and we've got time for some questions. And also, let me know if there's anything online as well, because I can't see the questions there. Mike?
Not so much a question, but a comment. Yesterday we heard a lot about data sovereignty and how those two are not mutually exclusive.
Yeah.
And I just wanted to kind of throw that out again.
Yeah, and I really appreciated that. Just because I'm sharing, or folks from the Indigenous community are sharing data openly, there needs to be credit given, especially when there has been work gone into doing that. And that's where building a culture of recognition is important, but also not losing control of your data. Just because data is open doesn't mean you're free to do anything with it. There are various licenses, and I know it's extremely boring to some people. Read up on the different open science and open source licenses, because there usually is a license that will really suit your purpose. Copyleft versus BSD clause 1, 2, and 3. You can have a completely open one, or you can have one that, no, I want to be indemnified by you using my data for an unfit purpose. Of course, this all matters that people respect that. So, for instance, for us, it's really, really important that the scientists we're working with get some credit, at least know how their data is being used. Does that kind of answer your, or does that speak to your point?
Absolutely, yes, thank you.
Yeah, I definitely agree. They are far from mutually exclusive.
So we know that open science is not actually free. And one of the big challenges is not necessarily developing the new techniques, the new usability pieces, because that typically there's great funding sources for those. But I think one of the grand challenges is funding the maintenance of some of these wonderful tools that have been largely adopted, because there will always be this need for care of whether it's the data itself or or the tools to analyze that data. Do you have any insight into what might be mechanisms over the next 5 to 10 years for supporting that maintenance and maybe small growth as opposed to the shiny new things that are easier to get funded in our current mechanisms?
So the great saying that open data sets and open source software, they're like dishes. They're only ever done if you never intend to use them again. So definitely for folks like me and you, Kevin, advocacy is super important. I've definitely learned that we've got to keep saying the same thing over and over again. One of the other things is really working hard to collect metrics on the usage of the things we're doing and showing them to decision makers, really metricing the impact of what we're doing. I can tell you a story from my own personal thing. When I first started on PyArt, I had to beg every year to get my funding allocation to keep that going. I don't have to beg anymore. Because there's going to be an article released by the Office of Science, signed off by the director herself, that highlights PyArt. So my funding agency is really happy with me right now, and that meta paper with 330 citations. I don't do this for personal glory. It is nice in my performance evaluation I can show this, but I take that and I can then show these papers, and I can do some basic arithmetic and show the millions, and I mean millions, tens of millions of dollars of research that PyArt has supported. So, and to kind of then flip it around to the other side of the generational gap here, teaching students those continuous integration, unit testing skills so we have a workforce pipeline of people who are keen to do this.
We do have to cut off questions there, unfortunately. Thank you, Scott, so much for that great overview. Very good lead into the next thing.